Today we're going to look at a couple of new vocabulary words. First one is concavity, C-O-N-C-A-V-I-T-Y, concavity of a function. And its graph. First of all, we'll start with the formal definition, and then after I tell you what the definition is, I'll draw you a graph of what the concavity of a function means, and I think it'll become very apparent after you see the graph. So first of all, the definition of concavity is a function is concave up. It's either concave up or concave down. So a function is concave up if the first derivative of the function f prime of x is increasing on an interval. All right, and then the opposite of concave up is concave down. So a function is concave down if f prime of x, or the first derivative, is decreasing on an interval. All right, so that's the definition of concavity, or concave up and concave down. And what this looks like graphically is this. Let's say we have a graph, kind of looks like a sine curve maybe. If we take a look at the derivative of this graph, let's say we're going to start here. Just take a look at the slope. This slope might be maybe -1. And then if we travel along this graph, we'll get down to this bottom point and the slope is 0. And then we'll move along up here, and then this slope might be, maybe 1/2. And then we come up to this point, and this point might have a slope of 1. So if we just take a look at all the slopes along the way, you can see that the first derivative is increasing. It's going from -1 to 0 to 1/2 to a 1. So this portion of the graph from here all the way up here is called concave up, because the slope goes from -1, keeps getting bigger, goes up to +1. All right, it's all about the slope and whether the slope is getting bigger or smaller. Now we reach this point right here where the slope was 1. And now if we travel along this curve a little bit further, we'll get up to this point and maybe the slope is 1/2 over here. And then we get up to this top point and the slope is 0. And then we travel along this way, and maybe this slope over here is maybe -1/2. So if you look at the slope, starting here, the slope is 1, then it goes down to 1/2, then it goes down to 0, and down to -1/2. So in this portion of the graph, f prime of x is decreasing. It's getting smaller and smaller. So this part of this graph, this interval, is concave down. And you can talk about the concavity as far as how the graph is being bent. That's not a mathematical definition, but a concave up graph, the curve is bent upward like an upright bowl. It's bent upward like an upright bowl. And you can kind of see that this is like an upright bowl. And sometimes they refer to concave up just casually as it holds water or some liquid, but we just say it holds water. So in other words, if you poured water into this, the water would stay in here because it's concave up. But if it's concave down, it's bent downward like a bridge. You can kind of see that this might be a bridge over water, right? So concave down, sometimes they casually refer to this as spilling water, or it spills water. So a graph will either hold water if it's concave up or spill water if it's concave down. So that's what it looks like. That's what the definition of it is. And then we can talk about the second derivative. The second derivative, or in other words, f double prime of x, is greater than 0 if the function is concave up. And f double prime of x is less than 0 if the function is concave down. Which brings us to another vocabulary word. Let me draw that same graph. No, let's just take a look at this graph over here. There's a point where the concavity changes. Looks like it's about right here. It goes from an up to a down. And this point right here where the concavity changes, it's called an inflection point. This point right there. So that's an important vocabulary word of the day too, inflection point. And I'll just write it over here. An inflection point is where the graph, or where the function, changes concavity, which means it goes from up to down, or from down to up. So an inflection point always happens when the second derivative is equal to 0. That would be a possible inflection point, but when the second derivative is equal to 0 and the concavity changes. From positive to negative, or negative to positive, which means we're going to talk about a sine table of a second derivative also. So then that's when you have an inflection point, but the second derivative has to be 0 there. So let's just take a simple example. Let's say f of x is equal to x to the third. We all know what that graph looks like from last fall. We could sketch that without a calculator. It just comes up and around like this. And let's describe the concavity. And find any inflection point. Oops, I spelled that wrong. All right, so what we're going to do is we're going to take f prime of x, which is 3x squared, and then we're going to take the second derivative, which is 6x. So the second derivative is 6x. Well, remember, an inflection point means that the second derivative is equal to 0 and the concavity changes. So if we set this equal to 0, second derivative equals 0, then we find x is equal to 0. So this is a possible inflection point. I write inflection point with an IP just so I don't have to write it out every time. So it is a possible IP, but we have to see whether or not it is truly an inflection point by doing a sine table for the second derivative. X equals 0, possible inflection point we're going to put on here. And now we're going to choose any number that's less than 0, put it into the second derivative, which is 6x, and see if it's positive or negative. Well, 6 times negative anything will give us a negative value, so we just put a negative here. And 6 times anything positive will give us a positive value here. So what this means is to the left or anything less than x equals 0, this is going to be concave down because the second derivative is negative. And then over here, anything greater than 0 is going to be concave up. So in this particular example, x equals 0, or this point right here, is an inflection point. And then this portion over here, and you can see that it would not hold water. This is concave down because the second derivative sine table told us that. And this point over, this part over here would be concave up. And what concave down would mean is the first derivative, which is the slope, is getting smaller and smaller and smaller and smaller and smaller. Now let's do a little bit, in the concave up, the slope gets greater and greater and greater and greater. All right, let's do another example here. Let's do f of x is equal to x to the fourth minus 4x to the third. Let's find concavity and points of inflection. Now, if you want to try this on your own, you can. You just go through the same process that we did for the x to the third graph. So the first derivative is 4x cubed minus 12x squared. And the second derivative is 12x squared minus 24x. So what we're going to do is factor this, taking a 12x out, and we're left with x minus 2, and set it equal to 0. And we get possible inflection points at x equals 0 and x equals 2. So now let's set up our second derivative sine table, x equals 0 and x equals 2. And then we're going to plug into the second derivative any number that's less than 0, any negative number. So what we're going to have is a negative times another negative, which will give us a positive value. So we have a concave up portion here. If we put in the number 1, we get 12 times negative 1, which is negative. And then if we put a value greater than 2, we get a positive times a positive, which gives us another positive. So this particular graph has 2 inflection points. It doesn't always work this way. Sometimes you get a plus, plus, minus, which would mean it would only have 1 inflection point, or sometimes you get everything that's plus or everything that's minus, but your job is to find the points where the second derivative changes from a plus to a minus or a minus to a plus. So we have this portion of the graph which is concave up. So let's just mark this as interval notation. We have from negative infinity all the way up to 0, and from positive 2 all the way up to infinity, which is concave up. And we have between 0 and 2, which is concave down. And we have an inflection point at x equals 0. Well, x equals 0 and y equals 0. So 0, 0 is one inflection point. And if we plugged in x equals 2, let's see, x equals 2 and y equals whatever 2 to the 4th minus 4x to the 3rd would be, let's see, 2 to the 4th is 16. 4 times 8 is 32, so it looks like it's 16 minus 32, which is negative 16. Maybe I made a mistake in my math. You can point that out to me tomorrow if that happens. So these 2 points, 0 and 0, 0, and 2, negative 16, are the inflection points of the graph.